Hello class, welcome. And today we're gonna look at the following ideas: horizontal asymptotes, vertical asymptotes, and rational functions. All of these are part of topic 2.8, which is rational functions and reciprocal function. Well, we started with reciprocal function, which is just the function 1 over x, and then rational functions. Okay, so let's see first what asymptotes are, horizontal and vertical. Let's see what these are. Okay, the first thing I want you to notice, guys, is the following. Whenever you hear the word asymptote, in your mind should appear the idea of a line, a straight line. Asymptotes are lines, are specific lines, okay? But they are lines. So we're gonna discuss these three examples, this function, okay, in red. This is the graph of my function f of x equals 1 over x, which you already studied on your own in the last lesson. Okay, this is known also as the reciprocal function, and its graph is known as the hyperbola, this in red. Okay, now I contend, guys, that these two lines that we see here, this horizontal line, which is represented by points together, okay, you don't have to understand that this is like too many points one after the other. All of this thing represents a line, but I decided to represent it like a dotted line in order to make a distinction between the graph of the function, which is this, and the graph of this line. Okay, so we have this horizontal line and we have this vertical line. This horizontal line is y equals 0. Okay, as you can see here, y equals 0. It's this horizontal line. And this vertical line is x equals 0. Okay, so I claim that this horizontal line and this vertical line, or these lines in general, are as asymptotes to this function f of x equals 1 over x. Why? Let's see. First, I want you to get a feeling to what this means. So if you notice, the first thing that comes to mind is the following idea. Let's first consider horizontal asymptotes. Only that one, okay? We're gonna go into vertical asymptotes in a moment. Let's first deal with horizontal asymptotes. I want you to notice this. I'm gonna choose a point in here. For example, this is a point 1, 1, and this point is part of this function, right? 1, 1. Because when you evaluate the function in x equals 1, you get f of x equals 1. So all of these points that I'm right now spotting or locating are also part of the function. Okay, and remember, one more time, the left coordinate is x, and the right coordinate in here, or the second coordinate, is the value of the function f of x. And I want you to notice what happens when we choose a point over the graph and we move it in this fashion, in this way. What I'm doing right now is moving the point from left to right so that it goes to infinity. That's how we say it in mathematics. This point is moving towards infinity, okay? It's going, it's going, it's going, it's going, it's going. Okay, I'm gonna do that again. And basically what I want you to pay attention to is these two values of, I don't have two cursors, so you have to forgive me about this, but I want you to look at the coordinates, okay? For example, right now, the value of x is 2, approximately, and the value of the function is 0.5. And as I move my x, or my independent variable, towards infinity, right now it's 3, and the value of the function is 0.3. Now x is 4, the value of the function is 0.25. Now x is 5, the value of the function is 0.2, etc., etc., etc. Okay, I'm moving x towards infinity. I'm making x approach infinity. And tell me, as I do that, as x is approaching infinity, in other words, as x is getting bigger and bigger and bigger, or greater and greater and greater, what is happening to the value of the function, to the values of the function? Can you see? What is happening to those values that you see as the second coordinate of these points? Look, it's 0.0.08, 0.07, 0.06, etc. You can see, I think it's pretty straightforward, that you can see that as x approaches infinity, or as x grows bigger and bigger, the values of the function approach 0, right? That is pretty clear. If we zoom in, you know, right here, my value of x is 20, and the value of the function is 0.05. And it's gonna get less and less. As I make x grow and grow, the value of the function will be less and less and less. But as you can see, oops, as you can see, it never goes below 0. Okay, it only approaches 0 more and more and more, but it never really touches that value. You see, it's getting less and less and less, but it never touches the value 0. Okay, so that's what is happening, guys. That's why we say that this horizontal line is an asymptote to this function. Why? Because as I make x approach infinity, in this case, what's going to happen to the values of the function is that they're going to approach a specific value, a specific number. It doesn't have to be 0, like in this case, okay? As I move x towards infinity, the values of the function are approaching 0. It doesn't have to be 0. In this case, it is. But as long as the values of the function approach a specific number, let's say 3 or -1 or whatever, then that means that this function, that this horizontal line is an asymptote. That is one way to see it. Another way to see it, I think a much better way. I tried the hard way to see it first. If you notice that these distances from your graph of your function towards the line that we are claiming is an asymptote, all these distances are getting less and less and less. Can you see? They are decreasing. They are decreasing. Well, you get the idea. Okay, you get the idea, right? They are decreasing and decreasing and decreasing. They will never be 0. They will never be 0. This red line that is representing my graph will never ever touch this horizontal line, which is the asymptote. Never. It doesn't matter how much you go towards infinity. Let me erase this thing. It doesn't matter. Look, it doesn't matter. If you think that at this point the red line has already touched the blue line, you're incorrect. Okay, because if I zoom in, look, can you see? And the same is going to happen no matter how far away from the origin I get. Right now I'm on x equals 100, and apparently what my eyes see is that the red line has already touched the blue line. But that's not a fact. If I zoom in, I can see that in fact the red line never ever touches the asymptote. And that is one of the properties of an asymptote. In most cases, or basically, because I don't want to confuse you, in all the cases that we're going to deal with, the graph of the function never touches the asymptote. That is one of the characteristics for some asymptotes, for the ones that we're going to work with. The graph of the function never touches the asymptote. There are other types of asymptotes that do not have this property, that the graph of the function can in fact touch the asymptote, but I'm just telling you this as a bonus, okay? We're not gonna deal with that. For all practical purposes, for us, an asymptote is a line that is never touched by the graph of the function, and with the property that as you get far away and far away from the origin and into infinity, the distances from the graph, these tiny distances that from the graph to the line, get less and less and less, progressively less and less and less. Now, if you notice, the same would have happened if we went in the opposite direction. What I did before was taking x and making it approach infinity, okay, positive infinity or plus infinity. Now I could have done the opposite. I could have chosen a point over here in this branch of the function and make x approach minus infinity. As you see, it's approaching minus infinity, etc., etc. It's going, and the same way, as we can see, the values of the function approach also 0. You see? Right now, x is minus 11, and f of x is minus 0.09. And then you can see that those values of f of x get closer and closer to 0. From the other direction, right? From now, it's approaching 0 from the left side, from negative numbers, but it's approaching 0. You see? So it's the same idea. Okay, so what is now that we have talked about this, what is a horizontal asymptote? First of all, it is a line. It is a line. With what property? With the property that once you make x, or your independent variable in your function, if you take that x and you make it approach either plus infinity or minus infinity, then the graph of the function will approach that specific line, or the values of the function will approach a specific number, okay? Or the distances, like I said before, the distances from the graph to the line are getting less and less and less, as you can see here, okay? That is what we know as a horizontal asymptote. Okay, what about this? Look, another function. We have this function f of x equals 2 to the x plus 1. This is an exponential function of base 2. And for this specific function, I claim that this line, this horizontal line, y equals 1, is an asymptote. For this function, this is an asymptote. Why? Let's see. We have my function here in red, one more time, and we have my line, which I claim to be the asymptote for this function, in a dotted blue line. Okay, so same idea. I take my x, I take any point over the graph, let's say this one, and I make it run towards infinity, or in this case, minus infinity, okay? I'm gonna zoom in a little, like so. And I'm gonna make it run towards minus infinity in this case. Okay, right now x is minus 3 and f of x is 1.12. Right now is x is minus 4, f of x is 1.06. Right now x is minus 5 and f of x is 1.03. And as you can see, if I perform this more and more and more and more, as x approaches minus infinity, f of x will approach 1. You see? But it will never really be 1. You see? So basically my red line, my red graph, is approaching the blue line, which is the asymptote, but it never really touches it. I know it looks like they're touching, okay? I know. If you look at from the distance, like from right here, for example, You may think that at this zone they already touched, but that would be just uh, an error, okay? Because if you zoom in, you can see that they're not touching, and it doesn't matter how far to the left you go. It doesn't matter. If you zoom in, I think the software is not giving me this. It doesn't have that much power. Let's see. Uh, Now I think by now they don't have that much resolution. Okay, I mean obviously computers don't have infinite resolution, but let's see at what point it starts to give me a difference. I don't know what it's doing. Minus 20. Let's see if here. No, it doesn't have that much resolution. At this point, the values between the graph, the red graph, and the blue line are so close. Okay, there it is. Can you see it? The difference is so tiny that I had to zoom in a lot in order for the difference to appear. You see? Look at the difference, guys. Right now we are at x equals minus 20, and you see the software is telling me that the value of f of x is 1. That is wrong. This is 1. This is the value of 1. This cannot be 1. But since the computer doesn't have that much power, I mean any computer, okay, they are finite machines. You cannot do everything you want with them. They're not showing me the difference. But you get the idea, okay? You get the idea. So that's what we mean by horizontal asymptotes. Now, on the other hand, a vertical asymptote, what are they? It's basically the same idea. For example, for my reciprocal function, the vertical asymptote is this, which is x equals 0. Okay? And in this way, how does it work? Okay, in this way, with a vertical asymptote, what you do is this. You're not going to run your x towards infinity or towards minus infinity. What you're going to do is this. You run x towards a specific number, in this case 0. I'm going to approach my x to 0. In this case, it's 0. In other cases, it may be a different number. So as I run my x towards 0, let's see what happens to the values of the function. Look at the right coordinates of those points. As x approaches 0, you can see that the values of the function shoot upwards very quickly, you see? Right now, x is 0.2 and the function is 4. Right now, x is 0.19 and f of x is 5.4 and so on. Okay, if I, this is hard to do. Okay, so as you can see, as x approaches 0, the value of the function shoots upwards very quickly. It starts to grow very quickly towards infinity. But again, this red line, the red graph, never really touches, as you can see. Look, it never really touches the vertical asymptote. No matter how far away from the origin, in this case upwards you go, it never touches the asymptote. Never. The distances grew less and less between the red graph and the vertical asymptote. Okay, look at this distance, look at this distance, this distance, this distance, and so on. Those distances are getting shorter and shorter, but they never get to 0. So that's how a vertical asymptote works. I'm going to show you another vertical asymptote. This one doesn't have a vertical asymptote, but this one does. Okay, this is your function f of x equals logarithm base 10 of x, and it behaves in this way. Okay, this is your graph. and right over this zone, it starts to go downwards very quickly. Again, you may think that the red line touches the asymptote, which in this case is also x equals 0, but they're not touching, guys. If you zoom in, okay, you may be thinking that they're touching. They're not touching. The differences may be very small, but they are there. You see? They are right there. They get smaller, the distances get smaller and smaller and smaller and smaller, but they are always bigger than 0, no matter how small, but they are always bigger than 0. You see? So that's why we say that this vertical line is an asymptote to this function, because the distances from the graph, from the red graph towards the line in case are getting less and less and less and less. Okay, so that's basically the idea behind this, guys, behind a horizontal asymptote and a vertical asymptote. That is the feeling, that is the intuition behind this. Of course, this is not, as I always tell you, this is not the most formal or the most mathematical way to approach these concepts. There is a formal definition, which, one more time, I'm going to give it to you as a bonus. It is not absolutely important or absolutely essential that you understand uh, the next bonus that I'm going to teach you about the formal definition for the asymptotes. But those of you who are interested in these things very much, be my guest, okay? So that's it about vertical and horizontal asymptotes. And now let's go to rational functions. Okay, and now to conclude the class, guys, we're gonna look very briefly at rational functions. And let's look at the definition. The definition says, we say that f is a rational function if and only if f of x equals p of x over q of x, where p of x and q of x are polynomial functions and q of x is different than 0. Remember that we never allow division by 0, and that's why we want to restrict q of x to be different than 0. Okay, so basically, I mean, definitions always sound more complicated than what they really are. So basically, what are rational functions? They are this. I'm going to give you examples. Okay, it's basically the division of two polynomials, and by now you should know what polynomials are because you have been working with them since first semester. Okay, for example, this polynomial, okay, of degree 2, okay, or a quadratic polynomial over let's say a linear polynomial 3x plus 1, then this f of x is said to be a rational function because it's the division of one polynomial over another polynomial. That's the first example. Second example, f of x equals, let's write a polynomial of order 5. I'm just inventing it, okay? Okay, this is a polynomial of order 5 because the greatest exponent of the x is 5 over a polynomial of degree 3. Okay, so x to the cube plus 2x squared minus x plus 3. Okay, so this is a rational function. Be aware, guys, that a polynomial don't have to have all the, like for example, this is a polynomial of degree 5, okay? That means that the greatest exponent of the x is 5, but that doesn't mean that you have to observe all the rest of the exponents, like exponent 4, exponent 3, exponent 2, exponent 1, and exponent 0, okay? Some of them may not be there. For example, look, I'm gonna write a polynomial of degree 3. You see? This is a polynomial of degree 3. Even if you don't see the x squared, any term with the x squared, that's perfect. They may be absent, okay? No problem. And now a polynomial of degree 2, 1 plus x squared. Okay, so this is a polynomial of degree 2, and they don't have to start with this one at the beginning, okay, and this one at the end. All right, so these are rational functions. It's basically one polynomial over another polynomial. And basically, guys, they look, when you graph these things, they look very similar to the reciprocal function. At least, I mean, they're gonna look more and more like the reciprocal function when you deal specifically with this type of rational functions. Look, we're only gonna work with this type of rational functions. Only of linear binomials, for example, this is a linear binomial over another linear binomial. You see? This is a perfectly good rational function, and these are the only ones that we are going to work with. We're not gonna work with any polynomials of degree 2 or above. Only degree 1, degree 1. We divide them, we get a rational function. Now, example. What about minus 5x plus 7 over x plus 1/2? You see, we have a polynomial of degree 1, another polynomial of degree 1, we divide them, and therefore we get a rational function. Another example, 6x over 1 plus x. Polynomial of degree 1 with no constant term, that is perfectly okay. And another polynomial of degree 1. We divide them and we get a rational function of the type that we're going to work with. We are not going to work with, for example, something like this. Okay? At least not in this topic, not in 2.8. Okay, and these functions, guys, look very similar to the reciprocal function. That is, they look like a hyperbola. Okay, and so I can convince you, I'm going to give an example of this. Look here, we have f of x equals 4x minus 1, which is a linear polynomial, over another linear polynomial or polynomial of degree 1, which is 2x plus 4. And we, as you can see, we have another hyperbola, which looks very similar to our original reciprocal function. You see, they look very similar. Okay, so basically, okay, yeah, another thing, they also have asymptotes. That is the only thing that we're missing, so we can finish the class. These functions, which are rational functions, also have asymptotes, and they are given in the following way. First, I'm gonna write it down. The y asymptote will be, this case 2, as you can see. Okay, this is the the horizontal asymptote, y equals 2. As you can see, the red graph, or our main function, which is the red graph, which is this one, the rational function, never touches its horizontal asymptote. Never. Okay, so you get the idea. And they also have a horizontal asymptote, which you can already imagine being over here. Okay, you can imagine actually that such vertical asymptote is going to be this line, right? What number is this? It's 0, 1, 2. It should be x equals 2. Let's see if that's true. There it is. No, sorry, x equals minus 2. Sorry, there it is. Okay, 0, minus 1, minus 2. So as you can see, this vertical line is also an asymptote to my main function. Why? Because such line gets approached by the graph of the function, but never touched by it. Okay, they only approach one another without touching. And ever more. The distances grow smaller as you go away from the origin. So, okay, now obviously that, I mean, I knew what the asymptotes were. Okay, I knew beforehand. How do you calculate them? How do you know how to calculate such asymptotes. Okay, in this way. Let's go back here. Remember, we will only work with this type of rational functions, only this type, f of x equals ax plus b, because this is a linear binomial of coefficient a and b over another linear binomial of coefficients c and d. So what are the asymptotes? The asymptotes are given by the following formulas. The horizontal asymptote will be the line y equals a over c. So you basically divide this coefficient over this coefficient and you will get the horizontal asymptote. Again, this coefficient over this coefficient. Let's see if that's true for the case that we just saw. Okay, we have here the horizontal asymptote. Can you see? It's y equals 2. And that should be equal to this coefficient of x, 4, over this coefficient of x, which is 2. 4 over 2, you get 2. Okay, so in fact, I don't know what that is. In fact, it works. And finally, the vertical asymptote. The vertical asymptote is given by the following formula, which is minus d over c. Minus d over c. So basically, the negative of this coefficient over this coefficient, or the coefficients of the polynomial that works as a denominator. Okay, minus d over c. Let's see if that's true for the case that we just saw. So in here, my vertical asymptote is this line, which is x equals minus 2. Is minus 2 the division of 4? Is minus 2 the negative of the division of 4 over 2? Yes, indeed. Okay, 4 over 2, that's 2. And then you put a negative in there and you get minus 2. So in fact, it works. Okay, so that's how you can get the asymptotes very easily with just these two formulas, which I'm going to explain the reason for them in the bonus, okay? And that's basically the whole thing, guys. That's it. Let's go for questions and doubts. And this is the whole lesson. Thank you.